Okay, let's go ahead and get started. I have posted homework 7, so you can read about that, binary tree program. We're going to have one more programming assignment. I'm going to be discussing it next Wednesday, and I'll release it then. The final assignment is worth 30 points. So it would be helpful if you could try to get ahead and work on this program 7 early if possible, so that by Wednesday, for example, if you had it done by then I think that the lecture I'm going to give on that day would be a little more meaningful, and you'd have a little more time to work on that 30-point homework that's the last one for the quarter. So our question of the day last time had to do with cooking, so that was our responses, mostly the sometimes, I guess, was our response. Today I'm going to be covering a topic that it's actually from chapter 10, but it's something that we skipped along the way. It's not a major topic. I mean, binary trees was the last major topic. This is kind of a minor topic, but it's something that's important to understand and something that we're going to use in the final programming assignment. It's also something that'll be on your final exam. This is a very practical thing that we're going to be talking about today, that we want to explain to you how to write a class that creates objects that can be put into sorted order, because there's a lot of built-in capabilities in the Java class libraries for putting things into sorted order. So this is also, in terms of what I do on the final exam, this is a question where I kind of get at just some basic class writing abilities. Mostly what we've been asking you to do is to write a method here, a method there, or kind of simulate what's the output of this code. So this is one of the few places where I ask you to write a complete class. So in a sense, what I'm testing on this final exam question is also just kind of having you show me that you know how to declare a class that has fields, that has a constructor, that has a toString, and so forth. So I'm going to go through an example today. It's a little bit simpler than what I would put on the final, but it shows you all of the kinds of elements that are involved. So I have in mind that I want to write a class to keep track of angles. And here I'm thinking of things like a latitude and a longitude, that you might express with degrees, minutes, seconds. I'm keeping it simpler by having just the degrees and minutes part, not having the seconds. But I've kind of put the initial version of it here that has our fields for degrees and minutes. Of course, we have a nicely encapsulated object by having private fields. In the constructor, I use the exact same names for the parameters, degrees and minutes. So that means that I get that issue of what's known as shadowing, that this parameter called degrees makes the field called degrees not visible inside of the method. And that's why I had to use the this dot notation in order to make it clear that I want to set the field degrees to the value that is in the parameter known as degrees. Remember that the most local definition is the one that takes precedence. So when we say degrees here, it's a reference to that parameter and not a reference to the field. I tend to write my constructors this way. Another thing that you could do is you could have called this something like degrees 2, and then you don't have the shadowing issue. Or, people come up with names like, some name other than degrees, something like that. So, and there are people who prefer to do it that way. A lot of people hate kind of this dot notation in the constructor. So it's a matter of personal choice. I don't care. You can do it either way. So you don't have to show me that you know how to use the this dot notation if you don't like it to do it that way. I think that one of the reasons that this is commonly done is that Jim Gosling, who was the designer of the language, tends to do this. So I think that he set a pattern early on that people have tended to repeat. But whatever. It doesn't matter to me whether you want to use a different name here, and then you wouldn't need the this dot notation. So I've kind of just set up this initial version. Let me go ahead and compile this version, and I've got some client code. So in the client code, I set up an angle object that represents 23 degrees, 26 minutes, another one that represents 15 degrees, 48 minutes. I make a list of these things. I add the two and print it out. So let's go ahead and compile and run this version. And we get angle, @ and then weird characters here that I've mentioned are a base 16 or a hexadecimal number. So what's going on, of course, is that we didn't define a toString method. So it has a toString method, though, that it inherits from the object class. We've seen this before, but that's kind of a crappy toString method that it gives you the name of the class, followed by an @ followed by this hexadecimal number that the Java documentation implies is the address of the object, but it's not required to be the address of the object. Anyway, that's not what we wanted anyway. And in basically all of these problems that I'd have you solve on the final, I ask you to introduce a toString method. So let's do a toString. And usually with these questions on the final, there'll be one or two things that are a little bit tricky to the problem. So sometimes the toString, for example, has some extra little details to it to get it just right. Here I have in mind a very simple toString method. So I'm just going to return the value of degrees plus a D, to kind of indicate that it's degrees, and then a space, and then I'll have minutes with an M. So D and M, I'm kind of using to indicate degrees and minutes. So let me compile this version and then come back over here and run this again. And we get 23 degrees, 26 minutes, 15 degrees, 48 minutes. And again, I've mentioned this before, but just to reiterate, on the midterm, we had this question that involved inheritance. And you remember that one of the important things there was to remember that if there was a call on a method, that we didn't just fill in what that call was going to do, because there was this issue of polymorphism. So for example, over here, when the println command is done, that's going to lead to the list asking for this to be turned into a string, and then the list is going to ask each of its individual elements to turn it into a string. So it's calling the toString method. And before, what we had was the bad version of toString, but it's important in terms of the power of polymorphism that we have the ability to override that, and it calls a different toString method. So that was, remember, something we talked about with the inheritance problem that we had on the midterm. Okay, well, another thing that I wanted to do was, and this is an example of something that I might do on a question like this on the final, is suppose I wanted an A3 angle that represented the sum of these two angles. It'd be nice to be able to say A1 plus A2. And there are some programming languages where you can do that, where you can give a new definition to the plus and say that this is going to call a method with the following name. So you have kind of the ability to do that. That's known as operator overloading. C++ is famous for having introduced operator overloading. It's a little bit crazy in C++ what you can do in terms of overloading. You can overload what parentheses mean, which is really leads to some, in some cases, some very odd things. The Java folks, when they saw what was going on with C++ operator overloading, they said, we don't want to do that. It's just, it's too much. So we know how you do this in Java, is that we have say a method. We saw this with like the letter inventory, that you can ask one of the angle objects to add to it another angle object. And the idea here would be that it returns a third angle object that represents the sum. The C# people, it's kind of interesting, at Microsoft, when they were designing that language, they decided to do something in between. So they did allow you to have operator overloading. Basically, you'd have an add method like this, but you'd say that I'm going to allow the client of this to use the plus, the familiar plus, and it'll call this add method. So C# kind of allows operator overloading, but a more limited kind of operator overloading. So they don't allow you to do some of the crazy stuff you can do in C++, but they liked having operator overloading. Java did not. So they just decided, no, we'll make you have a method called add, and you can't use the plus sign. So what would we do then? We're going to have an add method. Now the idea was that it makes a third angle object that represents the sum, and then it's going to return that. So its return type will be angle, and the method was called add. So I'm going to ask one angle object to add to it a different angle object. So if you were the angle object that I'm talking to, I tell you to add to you this angle object that I'll refer to as other. So there's kind of, you're one of the angle objects I'm talking to, like over here, I'd be talking to A1, and I'd be saying I want you to add to yourself the A2 object and return that sum as a brand new object. This is not changing A1 or A2. It's returning a brand new one. So I'm going to put in here, let's have some local variables. I'll call it D for degrees and M for minutes. Int M is something or other. And then I'll return a new angle object that has those degrees and minutes in it. So how do I know what the degrees should be? So I'm talking to you, say like you're A1, and I want you to add to your degrees the degrees of the other object. So how would you do that? Well, I can refer to just degrees, right? I mean, to get your degrees, we can just refer to degrees. And how about to get the other one's degrees, we can say other dot degrees. And we could do something similar with minutes, minutes plus other dot minutes. Now, but does that work? I mean, that's one of the questions, right? I mean, obviously, you have access to your own fields called degrees and minutes because, we're inside of the, an angle object that has degrees and minutes. So we can refer to degrees and we can refer to minutes to refer to the ones that are inside of this particular angle object. But how about referring to the degrees field of another angle object? Isn't it private? And so doesn't private mean that we can't do that? Wouldn't we need a get command? This is an interesting example. So I haven't introduced a get command yet. I mean, maybe there would be a get degrees and a get minutes that we would call, but maybe there wouldn't be. And then, the question would be, well, how would you do an add command like this if you didn't have access, if you didn't have the ability to do this? So I normally ask the class, what's going on here? Does it work? And we, make funny jokes about privacy and how is there real privacy in the world? There's a lot of controversy these days about what kind of privacy Facebook and Google and so forth provide. But in any event, the rule that's being applied here is a rule that we've mentioned before, but it's an important one for you to remember and understand, which is that private means private to the class. So there's kind of a relaxed atmosphere among all of the different angle objects that any angle object can refer to private fields of other angle objects. And this would be an example of where it would be important to be able to do that. If you didn't have a get degrees or a get minutes, you wouldn't be able to do this otherwise. So private means private to the class. Objects of other types are not able to access the degrees and the minutes, but a fellow angle object would be able to access degrees and minutes. So this is actually going to work. I did want to say that sometimes when I ask people for how to do this, I get the suggestion that we should do this dot degrees plus other dot degrees. Now you don't need to say the this dot, because we don't have any shadowing going on here. There's no local thing called degrees. So it's not like the constructor here where we needed to use the this dot notation, but we can use the this dot notation if we want to. Some people like this parallelism when you're dealing with two objects of the same type that you're manipulating somehow. They like to incorporate, kind of have it be a this dot a field versus an other dot a field. And if you like that, that'd be perfectly fine. I think that there's something to be said for kind of being able to see that very explicit parallel there between the degrees field of the other object and the degrees field of this object. I don't tend to do that. I mean, the rule that I tend to follow is if I don't need the this dot, then I don't include it. I mentally in my head know that that's this dot degrees and that's this dot minutes. So I tend not to do that, but it's, again, kind of a matter of personal choice whether you wanted to do that. Let me compile this version of the program, and then let me come over here and try. I meant to do something with this here. I meant to add my A3 to the list, so it should represent the sum of those two. Let's try compiling and running this version. And so we get a third angle object that's 38 degrees, which is the 23 plus the 15, and 74 minutes, which is the 26 plus the 48. So we get this third angle object that's 28 degrees, 74 minutes. And I normally ask people, is that okay? And people say, wait a second, degrees and minutes, you're not supposed to have 74 minutes because, there are 60 degrees in a minute. And so this is really, there's more than a degree's worth of minutes here. So we don't tend to say 74 minutes. We tend to want to move 60 of those minutes into the degrees. So that's something that we should be doing over here. I'm going to talk about this. I want to mention several things about it. One of them is I'm going to kind of start with the constructor and talk about what I would see as a precondition here. So, I would be very clear about this if this was an exam question. One of the issues, for example, is whether you need to deal with negatives. And I think I'm going to just keep this simple and say that degrees is greater than or equal to 0. So we're not going to allow negatives. And minutes is greater than or equal to 0. We're not going to allow negative minutes either. And what about this rule about the minutes is that you don't want minutes to be a really large number, because then that means that really you have, the degrees is set to the wrong thing. So what constraint would we want to have on minutes? Minutes is less than or equal to 60, but can it really be equal to 60? No, actually, if it ever became exactly equal to 60, that would be a full minute, right? A full degree, excuse me. 60 minutes would represent 1 degree. So we actually want the minutes to be strictly less than 60, between 0 and 59, to kind of be legal. So this isn't legal because it's 74. And I might ask you to do a check for that, on an exam question. It's nice to have a variety of things that I ask you to do on a question like that. It's a 20-point question on the test, so it's something that I expect you to take a good chunk of time to complete. And it's nice to have lots of little things that I'm looking for that you're just kind of verifying for me that you know how to do that as you're working on the final exam. So I've got 3 different things here that would make it illegal. These are the 3 reasons that requirements for a legal degrees in minutes. We want to describe the illegal version of it. So we kind of want the negation of all of this. I've been saying for a while now that Chapter 5 mentions what's called De Morgan's law, which is a convenient thing to understand when you're thinking about negations of expressions, Boolean expressions. So what De Morgan's law says is that the negation of this overall thing is that each of the 3 clauses gets negated and ands become ors. So what's the negation of degrees greater than or equal to 0? That would be degrees less than 0. The and becomes an or. What's the negation of minutes greater than or equal to 0? Would be minutes strictly less than 0. The and becomes an or. What's the negation of minutes less than 60? Minutes greater than 60. Is that the negation? No, you got to be careful. The negation of strictly less than is greater than or equal to. So that's kind of the way I would negate that. And so I could say if any of those things is true, then we would throw a new illegal argument exception. That might be something that I'd ask you to do. So this is going to kind of make sure that we don't construct an angle object that's inappropriate. And if I try running the code I had from before, now I get that illegal argument exception when it tries to make the angle with the 74 minutes in it, because that's an illegal number of minutes. So we're going to want to fix that. We don't want to throw an exception, especially one that we generated from our own code. But I wanted to mention another idea before we get to that. This is an idea that's discussed in Chapter 8, I believe, of the textbook, the idea of a class invariant. This is a good bit of terminology to be familiar with. We haven't really had the time to talk about this idea, but an invariant is something that you guarantee is always true. When I did the optional quicksort lecture, I talked about the idea of a loop invariant. This would be a class invariant, something that's always true of all of the objects of this type. And so you can kind of take these limitations on degrees and minutes. So I'm going to say degrees is greater than or equal to 0, and minutes, well, actually what I can do for minutes is I can kind of combine the two different things here and say that 0 is less than or equal to minutes, strictly less than 60. So minutes has kind of that relationship. It's always greater than or equal to 0, and it's always less than 60. So basically what I would be saying here is that this is a relationship that I want to guarantee is true of all angle objects. So I would consider an angle object to be in a corrupt state if the invariant was not satisfied. So I'm going to kind of enforce that myself. So I've made sure that when I go to construct one, that is so. And then what I would do is any other method of the class that changes the state, I guarantee that it maintains this invariant, that it preserves the invariant. Now here what's going on is that I would be constructing an angle that violates the invariant. So I've got to do something to fix up the minutes. So the question would be, how do I do that? By this point in the quarter, I usually get people who recognize that, the thing here was that minutes was too big, right? And this multiples of 60 are a problem with minutes because every one of those 60 minutes represents a degree. And so there's usually somebody in the audience who remembers that Stuart loves mod, that m mod 60 might be useful and m divided by 60 might be useful. And certainly that's a way to fix it up, and I'm very pleased that people would use that approach. But I actually wanted to kind of showcase the fact that you can do something slightly differently here. What if we had an if? So what is the problem here? What's the value of m that would be bad? And it would be an m that's greater than or equal to 60. If you've got at least 60 minutes, then that means that you've got a full degree's worth of minutes in there. So what would you want to do? You'd want to take that m and subtract the 60 minutes from it, and then do a d++. So you're basically moving 60 minutes from m into d. So you take away 60 minutes from the m, add 1 to the d, because that's a full degree's worth of minutes. And you might think to yourself, well, does that need to be a loop? Like, does that need to be a while? Will a simple if do? Well, it kind of depends, right? How big can m be? And maybe instead of a while loop, we'd use the mod trick, something like that. Well, this is a case where the invariant can come into play. So remember that the idea of the invariant is that we're gonna guarantee that this is true, and then that means that you get to assume it's true as you're writing code. So that means that degrees is at most 59, and minutes, is at most 59, and other minutes is at most 59. So the largest sum you could get is 59 plus 59, which is, I think, 118. It's shy of 120. So there could be 60 minutes worth of extra minutes that we have to account for, but there wouldn't be as many as 2 degrees worth, 120, because the highest sum we can get is 59 plus 59. So that would be a way to kind of apply the invariant to know that I don't have to worry about this being a loop. An if will be fine. The invariant kind of tells me that it'll be simple like that. That if there's a problem, there's only 1 degree's worth of extra minutes to account for. Well, let me go ahead and compile this and come back over here, and we'll run the code again. And now, instead of before, what we had was the 38 degrees and 74 minutes, and you'll notice the 38 degrees has now become 39 degrees, and then the 74 minutes has become 14 minutes. So that's good. That's kind of what we wanted it to do. Okay, so that's a little bit of stuff that I might do that's not related to the sorting idea that I wanted to talk about. Let me switch to the sorting idea. So let me uncomment this here. What I'm doing is I'm setting up a little two-dimensional array here where I've got some degrees, minutes, degrees, minutes, degrees, minutes, a bunch of specific pairs of numbers that I want to add as angle objects. I'll construct brand new angle objects and put them into my list so that I have some extra data to work with, not just these three, but these extra ones as well. And what this code does is it prints it out, it calls collections.sort, and then it prints it again. Now, we've seen that that for arrays, there's a class known as arrays that has methods like arrays.toString. There's also an arrays.sort, arrays.binary search. There's lots of interesting commands in the arrays class. Well, there's a similar class known as collections that has useful methods. In this case, this is a method for lists, you know, that we can call a sort, collections.sort on a list, and it'll put the list into sorted order. So what's going to happen when I go to compile this? Well, if you think about it, I mean, what have we told Java about an angle object? I mean, how does it know how to put these things into sorted order? I mean, it doesn't. We haven't told it anything about how to put it into sorted order. So I'm not sure what your guess is, but if I hit compile, I get an error message. No suitable method for the sort command. No suitable method found for sort of list of angle. It doesn't know how to sort a list of angle, is what it's saying. Well, that's because I never told it anything about these angle objects that would allow it to know how to put them into sorted order. So how do we do that? You may remember that when we did the merge sort lecture, right around the midterm time, that when we went to compare strings, we had to do things in a slightly different way. We had to call a special method known as compare_to. Well, Java has an interface that it has defined known as comparable of t. It's one of these generic interfaces. Some people like to pronounce that as comparable. I guess there's a battle within the Java community. Actually, I think it's almost evenly split between people who will say comparable and people who say comparable. I say comparable, so whatever, it doesn't matter. Whichever you prefer, maybe you'll wait and see what your TA does next week when they talk about this in section. But comparable of t, and notice there's tons of classes that implement the comparable interface, including things we've seen like integer and string. You know, so a lot of the classes that we've seen implement the comparable interface, and the comparable interface has one method in it that's called compare_to. So you compare to something of the same type. It's comparable of t, you compare to a t, and you return an int. So in order to be able to do what I was trying to do over here, where I could call collections.sort, I have to be using a class here that implements the comparable interface. Comparable of t was the way the interface was described. Now, for anything that I will ask you to do in terms of comparable, this t that you would fill in here will always match the name of the class. So if you're writing a class angle, it will implement comparable of angle. You don't always make these things match. I'm going to show you an example in Monday's lecture where they don't match. But that's getting into kind of more advanced object-oriented programming than what I'm going to expect you guys to have mastered. So for your purposes, in terms of anything that we do for the homework and anything that we do for the exam, whenever you're writing a class called foo, it will implement comparable of foo. So those things will always exactly match. So we're going to say that angle objects implement comparable of angle. If I hit compile, it gives me an error message. Angle is not abstract and does not override abstract method compare to angle. Well, you can't just claim to implement the comparable interface. You have to actually implement the comparable interface. So you have to have a public int method called compare to that takes an angle object other. So you have to actually have such a method. The rule for comparable, for compare to, was that you return a value less than 0 to indicate less than. You return 0 to indicate equal, and you return a value greater than 0 to indicate greater than. So if you're the angle object that I'm talking to, and I'm asking you to compare yourself to some other angle object, if you find that you are less than that other angle, then you should return a negative int. If you're equal to it, you return a 0. If you are greater than that other angle object, you return a positive integer. We have to deal with both degrees and minutes. Between the two, which one is more relevant? I normally ask, and people will normally point out, it's degrees that's more important, right? I mean, minutes could be really high, but that doesn't mean it's a large angle, because the degrees might be very small. So degrees being large is more important than minutes being large. So what I'm going to do is I'm going to deal with degrees first. I'm going to ignore minutes for the moment, and we'll fix that. But I'm going to just do degrees. So what you could do is you could say, well, I've asked you to compare yourself to this other object. You could see whether your degrees are greater than the other one's degrees, in which case you could return, not less than, greater than. I wanted to do the less than. Suppose that your degrees are less than the other ones. That's this first case. Then you're supposed to return a negative integer. Any negative integer will do, but -1 would be kind of the usual one to do if you were writing out an if-else like this. Else if degrees is equal to other dot degrees, then that means they're equal, and we would return a 0. And otherwise, that would mean that degrees is greater than other dot degrees. That's the only other possibility, and we would return, say, a +1 in that case. So we could write it in that way, where we return a negative, a 0, or a +1. Let's compile and come back over here. Now let's see what happens when we hit compile. Remember, it didn't compile before because it didn't like the call on sort. Now it compiled, and when it runs, it's going to show us, there were our original 3 angle objects that we put in there, and then after those 3, I added a bunch of other ones that were in that array called data. So this is what was in that array to begin with, the original order, and then this is what we get after calling sort. So notice that it's putting the 15-degree angle first, and then the 23-degree angle, and then a bunch of 30-degree angles. Now these are not in the right order because minutes are not being paid attention to. We haven't done that part yet, but 39 degrees is here. But it's getting them in the right order based on degrees, which was the part we were working on. Again, some people like to say this dot degrees, if this dot degrees is less than other dot degrees, which would be perfectly fine if you wanted to do it that way. I wanted to mention an idea that is a kind of programmer's trick. It's a good trick, though. It's used a lot, actually, in the Java class libraries. The string class uses this trick, for example, which is there something I can do that would be simpler than writing this great big if-else here? Is there some expression I can use for what to return that would be simpler than that? So I normally ask, and often I get somebody who kind of notices, well, if you were to subtract one from the other, so if I took degrees and subtracted other dot degrees, let's think about that. Suppose that your degrees are smaller, and you subtract other dot degrees, that gives you a negative integer. What if they're equal? That gets you a 0. And what if your degrees are bigger? That gets you a positive integer. So this little expression, degrees minus other dot degrees, gives you a negative, a 0, or a positive integer as appropriate in the exact same cases. So if I kind of compile this version, come over here and run it again, we can kind of see it's still working. It's still putting the 15 degrees first and then the 23 degrees and then all the various 30-degree ones and so forth. So that's a nice way to do it that would allow us to do it in one line. How do we incorporate the minutes? Lots of interesting ideas about that. One thing that people think to do, which is an interesting idea, is to compute total minutes. Instead of having two different numbers, degrees and minutes, you kind of turn it into the total number of minutes. And then you can just do this subtraction trick. That would certainly work, and that would get full credit. I'm going to do it slightly differently. I'm going to think about what is the case where the minutes matter. And the case where the minutes matter is when degrees is equal to other dot degrees. When the degrees are the same, we want to use the minutes to decide. And so what we can do is the same trick. We can return minutes minus other dot minutes in that case. And otherwise, what we can do is to return the difference of the degrees. So we can kind of have two different cases there. Let me go ahead and compile that version and come over here. We'll run one more time. And now it's doing the degrees in the right order, but now among the things that were 30 degrees, I've got the 8 minutes in front of the 12 minutes, in front of the 19 minutes, in front of the 45 minutes. Now it's sorting it right, even with the minutes involved. So that's going to be kind of my final version of that. I'll put it on the calendar for today so that you can take a look at it. And as I said, we're going to be going over some old exam questions in section on Tuesday. We'll also be revisiting some of this in a lecture that I'm going to be giving on Monday. We'll talk again about kind of the comparing stuff and sorting. So we'll see an interesting variation of this in the Monday lecture. All right, so that's what I wanted to tell you about what I call the comparable class questions. I've got enough time that I wanted to do one more thing with you, which is that all quarter long we've been doing things like making array int list, linked int list, int tree, where it's really you want array list of E, linked list of E, the int tree, tree map we want the generic version of those, the KV for the maps and so forth. So I've said to you that I was going to take one of our int versions and turn it into the of E versions. So that's what I want to do with you. So I've got here some code, search tree client, that I want to write. So I want to have a thing called search tree of E. So initially I want to be able to do search tree of string, and then later I'm going to want to be able to do search tree of integer. And I want it to do the right thing, like what the tree set does, so that basically when I'm dealing with strings, it's going to put them into alphabetical order, and when I'm dealing with integer, I'm going to want it to put it into numerical order. Well, so what I did is I took our int tree node class and I just renamed it search tree node. So obviously that's not going to work. We have to fix it up. But let's work on that then. So how do we fix it up? Well, we can do a fair amount of things just by doing a find and replace. So let me scooch this over a bit. So what I wanted to look for here, we have the int tree node, is the way this code is set up right now. I want to search for int tree node, and I want to replace that with search tree node of E. So I want a generic version of the node class where I can supply a type, like string or integer. So I can do, let's do a replace all, and that does a lot of replacements. It's too bad I don't have you guys here as an audience, because then I ask people for suggestions about what else has to change. And people normally notice, well, I can't do int anymore. This isn't the int tree, so the data is not going to be of type int. It's going to be of what type? We're trying to do the generic tree, where it's, search tree of E. So the data here is going to be of type E. That gets filled in with string or integer or whatever. And similarly here, that's going to be an E. And here, that's going to be an E. So those are changes that I have to make to this code. If I compile this version of it, I get an interesting error message. It's unhappy about this constructor, and it's pointing right after this of E in the constructor. Well, this is a kind of a minor detail about working with generics, which is, and Java could have kind of decided this either way, but you often say search tree node of E in many different places, but not in the header of a constructor. So when you go to have a constructor for the search tree node, you don't repeat the of E. So I'm going to get rid of that of E there. I'm going to get rid of the of E there. So we just say search tree node. We don't say the of E. Let me go ahead and hit compile. And it compiles now. So the node might be ready. We'll see. So then I've gathered together some of the code we have from int tree that we ended up with at the end of Wednesday's lecture. So we know that if we construct a binary search tree, we follow the binary search tree rule. That's the add method that we wrote last time. That if we then do an in-order traversal as our printing command, when you do the in-order traversal, it'll print it in sorted order. So that's kind of what I have here is the code from Wednesday for an int tree version of this. So how do I fix it up? Well, you might think that the first thing I should do is to replace all of the occurrences of int tree with search tree of E. And we're going to want to do that eventually, but that's not the first thing you want to do. The problem with making that the first thing is that then when you come across int tree node, it'll do a replacement there. I actually did this once when I was doing this work, you know, that this became search tree of E with the word node afterwards. So what we want to do is we want to be careful about that. Let me do the find and replace. We actually kind of have it all set up to do, we don't want the int tree there. We wanted to be, I'm not sure why it's keeping some of what I had there before and not others. JGraphs was doing something a little odd. The first thing we want to replace is not int tree, but int tree node. And we want to replace that with search tree node of E. So we want to fix up those things first. Oh, I think why the reason it's doing that is that I had int tree selected. That's why it did that. Okay. I understand now, because, you know, it was because I had selected some text there. Let me do replace all, and so I've got now my search tree nodes have been replaced. So now I can do that substitution where I replace int tree with search tree of E. So let's fix the ones that are the tree type. We'll do a replace all, and that's kind of what we'll do with the global replace. Remember that the constructor would not have this here. If we're adding to a tree, now we add something of type E. We wouldn't add an int, we'd add something of type E. I think otherwise that's the basic changes that we would make. If I hit compile though, I get an interesting error message. The error message says bad operand types for binary operator less than or equal to. So it's this line of code right here that's a problem. I'm going to make a copy of it so that I remember what it was originally, and then I'm going to kind of comment that out. So when it was a simple int, that was primitive data, and with a primitive data, you can see whether it's less than or equal to, right? But this is not primitive data, this is object data. So how do you do the comparisons for objects? It's like the string, it's like what we just did with the angle class. You have to use compare to. So you ask value to compare itself to root.data. And there's a rule of thumb that I mentioned in the merge sort lecture. I don't remember if you remember this rule of thumb, but if you had wanted a less than or equal to comparison, you know, if that's what you would have done with the primitive data, what you do here is you see whether the call on compare to returns something that's less than or equal to 0. So whatever relationship you were looking for here, you see whether the compare to has that relationship relative to 0. That's kind of a simple rule of thumb to follow to know how to turn a line of code like that into a line of code like this. So let's try compiling that version, and we get an interesting error message. Cannot find symbol method compare to E. So here the problem is that all that Java knows about this is that it's of type E. And it doesn't know anything about the type E. So as far as it's concerned, type E could be object. You know, it doesn't know anything more about it than other than just that it's like an object. In particular, it doesn't know that it has a compare to method. So that didn't compile. The compiler said, no, the object class doesn't have this method. It's just like your midterm question when we had a variable of type object and we tried to call method 1, method 2, method 3. The compiler rejected it. So the compiler is rejecting this because it says there's no such method. How did we get around it on the midterm? We used casting, right? So I'm going to do that here. I'm going to say to Java, well, I know I told you before that value was of type E. Well, now I'm going to cast to comparable of E. I'm going to let you know that it's not just an E, but it's a comparable of E. So I put this little thing in parentheses in front of value in order to let it know that I want to cast this to that. Let me try compiling. And actually, I think I end up with exactly the same error message as before, that it says value.compare to, it doesn't know about a compare to. You may remember that I mentioned this when we were first doing these inheritance problems for the midterm, that the dot has a high level of precedence, so you need an extra set of parens in here to force Java to do the cast. So I'm basically saying, look, here inside parentheses, I'm saying not value, but value being cast to comparable of E. So then I'm letting Java know, I'm kind of saying, to get past the compiler, I'm kind of saying, trust me, it'll implement the comparable interface. It'll be of type comparable of E. And so that call on compare to makes sense. So now if I hit compile, I get an interesting response. They're notes. So it's not an error. It didn't reject it. It just says this uses unchecked or unsafe operations. Well, we know that. We know that, this passed the compiler. This allows us to get past the compiler. But it may be that we give it data that doesn't implement the comparable interface. What would happen if it doesn't implement comparable? Well, then it would try doing the cast at runtime, and you'll remember from, maybe you've blocked it out of your memory, but on the midterm, you remember that if it doesn't turn out to implement comparable of E, then it throws a runtime exception. So that's what it's letting us know here, is that this is unsafe. This may cause a runtime exception when it's executed. The compiler can't verify that this is okay. That's what it's letting you know. But let me take this version, because it wasn't an error, it was just a warning. And then I compiled my client code. Oops, I didn't want to be here. I wanted to be in I wanted to compile my search tree client code. And then if I try running that, I could give it some names like Trump, Biden, Harris, Pence, Regis, for example, throw in a bunch of names, and it put them into alphabetical order, which is good. 3, 29, 7, 14, 42, -3, and say a 0. And it put those into numerical order. So it worked. Our search tree worked. So that version of it does work. It's unsafe, but it works. Well, I wanted to mention one last thing. I got a little over a minute before we get cut off, which is that there is another way to do this, which is that here when we say search tree of E, we can say not just any old E, but an E that implements comparable of E. That would kind of make sense that that's the way you would say it. We're adding an extra little clause here that adds a constraint to the E. Not just any old E, but an E that implements comparable of E. Well, they didn't want to make the distinction between inheritance and implementing an interface, so they use the extends keyword. So it always uses extends, whether it's an interface or whether it's inheritance. But the idea is the same. And what it means is that we can go back to our original version of this code that we had in the middle here, where we were saying value.compare to. Now that it knows that E implements the comparable of E interface, now I don't need the casting. And it's not unsafe. I'll say actually a little more about that in Monday's lecture, but I think we're about to be cut off here, so that's a good spot to end for today. And we'll do more on Monday.